Okay, so in this tutorial, I'm going to teach you how to embed machine learning models into your Bubble application. Now, this is a bit more of an advanced topic, but it's a fascinating topic, so I encourage you to stick with me until the end, because learning how to embed machine learning logic into your applications is nothing short of a superpower. Now, the truth is that generative models, at the moment anyway, get the majority of the media attention. Now, these generative AI models do things like create text, videos, images, and so on, and while these tools obviously are spectacular in their ability, an arguably more important and spectacular process happens when we don't get our applications to generate something for us, but instead we get them to think, to learn, to decide, as well as to predict. Now, any industry which can benefit from spotting patterns in data and being able to predict outcomes with high levels of accuracy would benefit from machine learning integration. So let's jump in now and learn how to integrate machine learning into our Bubble apps. Okay, so we're going to use a plugin that we recently developed called Nebulum Machine Learning, which is an ML plugin built on top of TensorFlow. Now, keep in mind that this is a premium plugin. It's one of the more complex plugins that we've created at Nebulum. So this is a small price to pay for this level of predictive capability. So to install the plugin, simply go to your plugins tab in Bubble and then search for the plugin here. Just type in Nebulum Machine Learning and you'll be able to install it right away. Okay, so once installed, you'll have access to many different machine learning models. So for example, you'll have access to classification models, regression models, anomaly detection models, forecasting models, and much more. You can search for all of these models over in the sidebar here. And don't worry if you don't know what all of these model types mean right now. We're going to unpack all of this as we progress through this Bubble machine learning tutorial series. Today, however, I'm only going to be talking about classification. So let's add our classification model onto our canvas here. Now notice that there are not any settings that need to be added to this element. All adding this element does really is just give us access to the classification actions, which are over in our workflow tab. So notice now that I can go to my workflow tab and then search for things like train, evaluate, and predict. However, let's not get ahead of ourselves here. Let's talk about what classification is before we learn how to use this plugin. So classification is a machine learning technique that teaches a model to sort things into categories based on patterns in data. Now that might sound boring, but as you're about to see, it's really anything but. It powers some of the most valuable systems in modern society. In finance, models can classify credit risk, detect fraud, predict customer churn, and even future equity prices. In healthcare, they estimate disease risk and patient readmission. In education, these models can predict student performance and dropout likelihood. In science, they can classify species and experimental outcomes. In streaming or e-commerce platforms, these ML algorithms learn what you like and then will recommend what you should watch or buy next. Nearly every industry benefits from the ability to predict outcomes from patterns in data in some way. And there are really no limits to what these models can do. Okay, so let's jump in here and get to work. Now, I've provided a link below to our machine learning plugin demo page where you can see the different models that we have over in the sidebar here. Now, by default, we're on the classification model, and you'll see this image of the Titanic off to the right here. Now, this is the classic ML classification example, which helps illustrate how classification and prediction in general works. Now, the Titanic dataset is ideal for demonstrating classification because it's intuitive. For example, everyone understands survival prediction. It contains mixed data types, both categorical and numerical. So for example, categorical data are fields like gender, these text-based fields here, while numerical data are things like age, which you see here. Now, similarly, this dataset is small enough for quick training, yet complex enough to showcase real machine learning techniques. Okay, so at a high level, let's see how this actually works. So classification models fall under a category of machine learning called supervised learning. And that simply means that we give the model examples where we already know the answer. So in other words, we provide feature data. These are the inputs. In this example on the page here, these input fields here under our training step are our feature data. These are things like gender, class, and age. Also, we provide the targets. These are the outcomes we want the model to learn to predict. In this case, it's the input field down here where we list if the passengers survived or died. Now, when we visualize machine learning models, they're typically presented like this, a fully connected network. Now, these first nodes on the left are our features or our inputs, the raw data that we feed into the model. The last node or nodes on the right are going to be our targets. This is what we're actually trying to predict. Now, in this tutorial, we're only going to be focusing on these features and targets, the entrance and exit points of our model essentially. But you might be wondering, well, what about everything in between? So these middle nodes form what we call hidden layers, and this is where the real magic happens in machine learning. You can kind of think of these as the model's internal thought process, the place where raw inputs get transformed into meaningful predictions. So within our plugin, I can drill into this training action here, and then you'll see the hidden layers property right here. So for example, here I have 2 comma separated values, which means that I want to use 2 layers. And the first layer here would have 64 neurons, and the second layer here would have 32. But again, I don't want to get into this too deeply right now, but I did quickly want to give you a top-level overview of just kind of what's going on. So here's what's happening in this middle section here. Each hidden layer is learning to detect increasingly complex patterns. So the first hidden layer might learn simple things like this passenger is female or this ticket is expensive. The next layer combines those simple patterns into more sophisticated ones. So for example, wealthy female passengers, or deeper levels might even detect even more nuanced patterns like wealthy female passengers traveling with small families in first class. Now these hidden layers are called hidden because we don't directly tell them what to learn. They figure it out automatically during training, adjusting thousands or millions of internal connections until they find the combination that best predicts the outcome. It's like the model is building its own internal logic or its own internal way of thinking about the problem. Now, in upcoming tutorials, we'll dive deep into these hidden layers, how many you should use, how many nodes should be in each layer, and what's actually happening mathematically as data flows through them. Now, we'll explore concepts like activation functions, backpropagation, and why deep learning is actually called deep in the first place. But for now, just know features go in, predictions come out, and the hidden layers are where your model learns to think. Now, as a side note, it's essential to understand how features map to targets within our plugin, or how inputs map to outputs. Now, the first item in each list all represent the first passenger in this example. So in this case, we're working with a male passenger in third class who is 22 years old, who had 1 sibling or spouse on board with them. And then here, below these values, we have this passenger's target, or we can also think of this as the outcome or exit. Now, as you can see here, this passenger died. Okay, let's head back up here for a moment. Now notice that the next passenger here is represented by the second value in each list. So this passenger was female, she was in first class, she was 38 years old, had 1 spouse or sibling on board, and their target or outcome was survived. So when working with this machine learning bubble plugin, you always need to make sure that your data maps properly. Also, it's essential that each input field contains the exact same number of values. You can't enter 50 comma-separated genders and 100 comma-separated classes. The ML model will throw an error if your counts aren't all the same. Okay, so now that you know how to format and how not to format your data, let's continue here. Now keep in mind that the model doesn't memorize the examples that we're feeding it here. Instead, it's going to learn the mathematical relationships, patterns, and how features map to targets. It builds an internal representation that lets it generalize to new data that it's never seen before. And I want to dive into this a little more because this is where I see a lot of people get really confused when working with machine learning models. So this is not like working with LLMs or other forms of AI where you enter an input and almost immediately get your output. With classification machine learning models, there are actually 3 stages of development. There's training, evaluation, and prediction. You see each of these steps right up here, step 1, step 2, step 3. So when working on this page, it's essential to remember that you can't evaluate or predict until you've trained your model. So you need to run the first training step before you can run the second or third steps. Also, as a side note, in this demo, after running step 1, we're just storing the trained model in the browser, which allows you to run the evaluation step as well as the prediction step. However, our Bubble plugin allows you to save these models to your database and then load these models whenever you want. So you don't always need to retrain a model before making a prediction. Okay, so now keep in mind that during training, you're not actually predicting anything yet. Training is when the model learns from the data where you already know all of the answers. In this case, all of our answers are down here in this input field. Think of it like this. You provide the model with a complete data set, all of your features, which are these inputs up here, and the target column, this input field here. You're essentially saying, Here are 100 examples. In each one, I'm showing you the inputs and the correct output. Now figure out the pattern that connects them. The way I personally like to think about this is kind of like a student taking a test. But imagine the student gets to see the answer key, but only after they've answered each question. So here's how it works. The model looks at the first example's features and then makes a guess about the target. Then, and only then, it checks the actual answer. If it got it right, especially with high confidence, it gets rewarded. Well, more on this word rewarded in a moment. If it got it wrong, or if it was uncertain, it's going to be penalized. Now, the model adjusts its internal understanding slightly based on that feedback loop. On the very first pass through the data, the model doesn't really know anything yet. Its parameters are randomly initialized, so its predictions are essentially just random. The entire point of that first pass is to measure how wrong these predictions actually were. So the model can then start to adjust on the next pass. Then it moves to the next example in the training data, and it just repeats this process. But during the training stage, the interesting thing is that the model can take the test over and over again, dozens, hundreds, even thousands of times, continuously refining its understanding with each pass through the data. Now, we call each complete pass through all of the training data an epoch. Now, mathematically, what's happening here is something called gradient-based optimization. The model is following the slope of the air surface towards its minimum. So let's set the number of epochs within our training model here. All we have to do is click on the button here. Next, you can add the training step by searching for the ML classified training step here. Now, I already have it added, so I'll just drill into my action here. Now, within this action, you'll see where you can add your categorical features. So to keep yourself organized, you can add the name here and then simply map the values to the corresponding input field in your front end. So for example, this gender category is simply mapping to this input field here over in our front end. So for our numerical features like age, we just need to scroll down a bit here, and then we'll see that we can add our numerical features down here. Now, one of the most powerful things within our plugin is that you can add up to 25 categorical features here and 75 numerical features for a total of 100 features. So if we scroll down a bit here, you'll actually be able to see where we can add our target value as well. Now remember, the target value is the value that we're trying to predict. So in our training step, we're feeding it the answers that we already know. In this case, we're mapping our target field here to which passengers survived or died in the front end over here. But what I'm trying to get to here is actually the number of epochs, which you can set right here. Now, within the Bubble Machine Learning plugin, we've also included very comprehensive documentation for each field to help you familiarize yourself with what each field controls. So with all of these values entered, let's train this model quickly by clicking on this button here. Now, let's ignore all of these other fields for a moment, but just notice that the model is displaying our features here as well as our target value right here. Okay, so far so good, but what are all of these other fields? So for example, what is loss? Well, loss is sort of your model's report card. It's a feedback mechanism which is communicated through something that we call in machine learning the loss metric. Now, loss is essentially your model's score for how wrong it was. Low loss means the model is making accurate predictions with high confidence, where high loss means that the model is either getting answers wrong or is very uncertain about its predictions. Now, under the hood, this penalty isn't arbitrary. It's often logarithmic, which means that confident mistakes are punished exponentially more than uncertain ones. Also, previously I said that the model rewards itself for correct prediction, but technically that's actually not right. But it was helpful in the moment to make the concept clear. But the truth is that there is no reward signal in ML classification. The model is not being praised for correct answers, it's only being penalized for error. Training then is not about maximizing reward, it's about continuously adjusting the model to reduce penalty step by step. So these algorithms are not getting rewards, they're just penalized less for better and stronger predictions. Now, the model's goal during training, therefore, is to minimize this loss, to get as close to a perfect score as possible. And it doesn't start with low loss. Training is an iterative process where the model gradually adjusts its parameters to drive this loss metric down. So again, if we were to train our model, we would see our loss show up right here. And here's the interesting thing. Now, our plugin uses TensorFlow, and TensorFlow was developed by Google, and the ML models that they developed run in your browser. Now, this is actually a double-edged sword for Bubble developers, because the issue here is that all of this machine learning training, all of this thinking and decision-making happens kind of at this abstract level under the hood. I personally think that working with machine learning models requires a greater ability for abstract thinking. You can contrast this with single-step generative models, which create something that the user can immediately see the outcome of. But with machine learning models, the only thing that is being generated are the results of the machine's learning or thinking. And with machine learning, it's not just about monitoring the output or the machine's decision, it's also about monitoring its thinking process. And this can be quite hard to do, actually. So what we've done at Nebulum to make this process much easier for you is we've added visuals and messages to the console so that you can watch the training, evaluation, and prediction process unfold in real time. So for example, we can train the model by clicking on this button and then we can see the results right here. But what if you wanted to see the actual learning process? Well, simply refresh your page and then press F12 on your keyboard to bring up the developer console and ensure that the console tab is selected here. Now click on the train button again. Notice now that you can watch the training process as it happens live, and you'll see the loss being reduced and the confidence being increased epoch by epoch. We've also built in the same console visualization for both the evaluation action as well as the prediction action. So we're not just storing the final values as states within our pop-up here, but we're also allowing you as the developer to view what's happening under the hood during the thinking process or during the training process. Okay, so I just touched on the concept of confidence here, and we see confidence also show up in our pop-up here. So what is confidence in the world of machine learning? So the concept of confidence is actually another area where I see a lot of people who are new to machine learning get quite confused. So let me help you understand this a little better. So when training, it's important to remember that the model doesn't just make a prediction. It also reports how confident it was with the prediction it made. So let's say we're predicting survived or died. So the model might predict died with 95% confidence. So it's very sure. Or it might predict died with only a 55% confidence, barely leaning one way or the other. So the penalty system or loss system cares about both correctness and confidence. Okay, let's look at a few examples to make this crystal clear. So imagine that we have a prediction which is both correct and comes out with high confidence. So for example, here, the model would suffer only a small penalty. So as you can see here, it's not a reward. The model is just receiving a smaller penalty for being more accurate. So the example here is that the model predicted died with 95% confidence, and the actual answer here was that this passenger died. So the loss in this case might be something like 0.05. Now imagine that we also had another correct prediction, but this correct prediction came associated with low confidence. So in this case, the model would suffer a moderate penalty. So in this case, again, the model might predict survived, but it only predicts survived with a 55% confidence. The actual result here is that the passenger survived, and therefore the model might penalize itself by giving it a loss score of 0.6. Essentially what it's saying is that you got it right, but you were barely sure, and that's just not good enough. Okay, so let's imagine that the model was now wrong with high confidence. So in this case, it would suffer a large penalty. For example, imagine that it predicted this passenger survived and it was 95% confident, but the actual result was that the passenger died. So in this case, the model might be penalized with a loss of 2.95, for example. Essentially, what the model is saying is that you were confidently wrong, and that's the worst kind of mistake that you can make. And here we have another example where the model might be wrong, but in this case, it's wrong with a low confidence. So in this case, it would suffer a moderately large penalty. So for example, imagine that the model again predicted survived, but this time it only predicted survived with a 55% confidence, where the actual result was that this passenger died, and therefore the loss might be something like 0.8. Essentially, the model is saying, look, I got it wrong, but at least I wasn't sure. Now, the model learns to be both accurate and appropriately confident. And here's another piece of the puzzle that confuses a lot of people about machine learning. You can't just train a model and then immediately use it for predictions. There's an important step in between called evaluation. Now, this is the second step that you see on the screen here. Essentially, during this step, you can evaluate your trained model before you use it for actual predictions. Your training and evaluation steps 1 and 2 here, serve very different purposes. So in training, essentially what's happening here is that the model sees the features, makes predictions, checks the answers, and updates itself. It's actively learning and changing its internal parameters. The goal with training is to minimize loss on the training data. Next, we have evaluation. Here, again, the model sees the features, it's going to make a prediction, it's also going to check the answers, but here it does not update itself. Essentially, it's being tested on data that it hasn't seen during training. Notice here in these input fields, the data is complete data with both features and targets, but the values are different here compared to the values used in the training data. So for example, here in my evaluation step, notice that my third passenger is male, but my third passenger in my training data was female. So all of these values are now new values within this evaluation step. And the goal within this evaluation step is essentially to see if the model can generalize to new data. Think of training sort of like studying with practice problems where you can check your answers and learn from your mistakes and constantly improve yourself. Where evaluation is like the actual exam. You do not get to revise your knowledge anymore, you just have to perform. And this is critical because a model might achieve perfect scores during the training data step simply by memorizing every example. But when you test it on new data during evaluation, it might fail miserably. And this is called overfitting, where the model essentially memorized instead of learning the underlying patterns. And that's why we always hold back some data for evaluation, data that the model has never seen during training. And this tells us whether the model truly learned generalizable patterns or just memorized the training set. Now remember, the model never peeks at the answers before making its prediction. So during both training and evaluation, here are the steps. The model will see only the features. The model will then make a prediction, and it will make that prediction with confidence. The model then will check the actual answer. Then the model will calculate its loss, which remember is the penalty. And then in training, the model will adjust itself to do better next time. And during evaluation, the model just gets scored. It's not allowed to adjust itself. So this process, predict, check, learn, repeat, is how the model discovers the hidden patterns connecting your features to your targets. And after enough iterations, these models can generally become so good at finding these patterns that they can make accurate predictions on completely new data that they've never encountered before. And that's when you know training is complete and you have a model ready for real-world prediction where there is no answer key to check against. And this is really the thrilling moment when your algorithm can kind of step out of your sandbox and into reality. And that's also when we move into this third step, which is the predictive step. Okay, so here, for example, I can enter a new passenger by entering their gender, class, age, and number of siblings, and then I can click on predict. And as you can see now, this male passenger from third class is predicted to die. And this aligns with the actual patterns discovered in this historical data set. Now, what makes this fascinating is how the model has learned the hidden social dynamics of that tragic night. Now, women and children had dramatically higher survival rates. The women and children first protocol was real and measurable in this data. So first-class passengers were also significantly more likely to survive, not just because of wealth, but because of proximity. So for example, they were closer to the lifeboats. They also had better access to information about the emergency and were also nearer to high-ranking officials who controlled lifeboat access. Now, even more intriguing here is that this model picked up on family dynamics that historians have debated for decades. So for example, large families tended to have lower survival rates. So the prevailing theory here is that coordinating 5 or 6 people in a chaotic, dark, sinking ship actually proved to be nearly impossible, while couples or small families could move quickly and decisively. Now, the algorithm discovered what survivors' testimonies suggested. In disaster, smaller groups had an advantage in this case. Now, this is the power of machine learning. It finds patterns humans might miss, and it quantifies intuitions that we've always had. Now, humans are remarkably good at spotting patterns, but only in low dimensional space. We can easily visualize data on a graph with an x-axis and a y-axis, so for example, 2 dimensions, or even imagine a 3D scatter plot rotating in space. Our brains evolved to navigate a 3-dimensional world, so we're naturally equipped to see clusters, trends, and outliers when data fits in 2 or 3 dimensions. But here's where we hit our cognitive wall, or here's where we lose the thread. The moment that we add a 4th dimension, our human intuition breaks down. We simply cannot visualize or mentally process what's happening in 4-dimensional space, let alone 10, 50, or 100 dimensions. Try to imagine a shape that exists in a 100-dimensional space. You can't, and none of us can. This is precisely where machine learning reveals its superhuman capability. While my Titanic example uses just 4 features, gender, class, age, and siblings, this plugin can actually accept 100 features simultaneously. That means it's effectively thinking in a 100-dimensional space, something no human brain can do. Now, imagine we could track not just gender and class, but exact ticket price, cabin location, number of parents aboard, exact boarding port, specific crew member interactions, proximity to different decks, time of boarding, previous sailing experience, nationality, profession, traveling companions, age, and luggage weight. And imagine we could do this all at once. Now, a human analyst would drown in this data. They would not be able to see which combinations matter. But the algorithm, it processes all 100 dimensions simultaneously, finding patterns like third-class Finnish passengers with moderate luggage who boarded in Southampton and had exactly 2 siblings had a 23% survival rate, for example. Now, these hyper-dimensional patterns are invisible to us, but crystal clear to the machine. And this is the true revolution of machine learning. It doesn't just work faster than humans, it operates in a dimensional space we cannot even perceive. So we still have a lot to cover. In this tutorial, we only covered classification, but in the next tutorial, we'll dive deeper into regression. And understanding the difference between these two is fundamental to machine learning. Think of it this way. Classification answers which category, while regression answers how much. So in our Titanic example, we used classification because we were predicting discrete categories, survived or died. The answer is binary, one or the other, yes or no. Classification is perfect when your outcome falls into distinct buckets. So for example, spam or not spam, cat or dog, approved or rejected, and so on. Now, regression, on the other hand, predicts continuous numerical values. So instead of asking, will this passenger survive, which is a category, regression asks questions like, what will this house sell for? Or how many inches of rain will fall tomorrow? Or what will the stock price be next week? The answer isn't a category, it's a number that can fall somewhere along a continuous scale. So as you can see, this is a big and fascinating topic. Too much, obviously, to fit into one tutorial, so I'll link to the next video in this series below. And lastly, if you find all of this talk on machine learning interesting, but you're not a do-it-yourselfer and you'd like to work with a team that can build out complex machine learning applications for you, be sure to head over to Nebulum and click on Contact in the top navigation bar. Simply fill out the form on that page and let us know more about what you're trying to build. Even if you're just pressure testing an idea, we'd be more than happy to chat with you about it. So that's all I have for you. Thanks for stopping by.